Greetings friends, my name is John Gabriel and this is the New Calculus channel. So today I'm going to be talking about Book 1 and Proposition 3, but before I do that I'm going to cover a small part of Proposition 2, which I forgot to cover in the last video. So let's begin. Now, remember Thomas Heath said that the case that Euclid covered was just a special, was the hardest case, which is of course absolute nonsense. And he obviously didn't know what he was talking about, because it doesn't matter how I do this, the proposition holds true, okay? What this means is that given any point A, okay, and any line segment of any length, you can create a line segment at that point A with the same length as this line segment. So I did put a little note, I pinned a little comment in the old video that you can actually move these around, and you'll see that the result holds no matter what you do and where you are, okay? So in other words, it's true for any particular case. So Thomas Heath obviously didn't know what he was talking about there. Right, so let's get rid of that. Actually, before I do that, Proposition 3, this proposition, should have appeared before Proposition 2, because what it says is that given any line segment C and a longer one, AB, you can cut C out of it. And the way to do that is very simple. You construct a circle with a radius that has this length, as you see here, this radius, and then of course you can see that the circle will cut this line or separate this AB distance so that you have a E distance equal exactly to C. Now remember, when we talk about straight lines, we're talking about distances. When we talk about any geometric object, we're talking about distances. We're not talking about anything else, okay? So bear that in mind as you do it. So the method here is very simple. You just draw a straight line like this, AB, and then construct a circle with center at A and radius equal to C. So that's how simple Proposition 3 was, and that's what Euclid should have covered before he wrote down Proposition 2, because that's really effectively what happens here. If you see the constructions here, there are many of them that are done with circles. First of all, he uses Proposition 1, which says that you can create an equilateral triangle, and then he uses the same technique to create this line equal to that line. Okay, so without further ado, I want to just cover some other important points. Now, you've obviously been brainwashed to believe that this object here is a point. Okay, it's not a point. It's a visualization of a point. It merely denotes the idea of location or place. And of course, you cannot say that a line consists of points, because that's like saying a line consists of nothing, which is totally garbage, because the main attribute of a line is distance. So what do we mean when we say points along a line? Well, we mean a location along a line, or a distance in two-dimensional or three-dimensional space. Okay, we talk about distances. That's what we mean when we say points, right? Now, it's also false to say that a real number corresponds to a distance along the number line. So you can't say that pi is a real number that, appears somewhere around here, because pi is not a number at all. It's a magnitude, okay? And so perhaps a correct statement would be to say that every magnitude corresponds to a distance on a number line, okay? So some distance, and a lot of those distances cannot be reified. And for this very reason, I'm going to put a link to an article in the details section explaining to you what it means to reify a number line, because believe it or not, even your stupid math professors don't understand that, okay? They don't understand that there is no valid construction of real number. Oh, don't worry, I know they've taught you about Dedekind Cuts and Cauchy Sequences and real analysis. That's all bullshit, okay? It's hand-waving nonsense. They've never understood any of that. And so all they're doing there is they're pushing myths onto you because they've never understood it and they don't know what they're talking about. Okay, and so what do you expect when an orangutan, you have an orangutan as your math lecturer? Are you ever going to understand mathematics? Never. It's never going to happen. Okay, so I do know better and I'm explaining these things to you. So all these objects here, they are not what you think they are. This here is not a circle. It's just a visualization or an instantiation of a circle. And what it means is that it's a special kind of distance with symmetry. It has symmetry around the diameter, and also the path falls completely in any given plane. It cannot stretch across different planes. So when you hear idiots talking about Riemannian geometry, which is also a load of BS, because the geometry comes from Euclid, and there's no different geometry to the geometry that Euclid uses. All geometry is Euclidean. Okay, so when you talk about parallel lines, you cannot apply that concept to a sphere because it's a concept that applies to a plane. And that's why the morons in mainstream got all that stuff wrong about axioms. They believe that the 5 requirements are axioms, but they're not axioms of any kind. Okay, and they can be proved systematically. As I've shown in my fine article, there are no axioms or postulates in sound mathematics, for which there will also be a link in the details section. So, I think I pretty much covered everything. I'm going to leave it at that, and probably I'll cover proposition 5, because I've already covered proposition 4, and I'll see how I feel. Maybe I'll carry on doing more videos on Euclid's elements, or not. I'm John Gabriel, and this is New Calculus Channel. Till next time, goodbye.